Hello friends. In the last lecture for deriving the governing equations of convective heat transfer, we used the control volume approach, and in order to keep the derivations simpler, we did the derivations for a two-dimensional control volume, which basically is a plane in a rectangle in the plane of the paper, and in the third dimension we assumed unit depth and therefore the volume was delta x multiplied by delta y multiplied by unity, and the surface areas on the sides would have been delta x into 1 or delta y into 1. And after deriving the equations, we were able to easily replace the third dimension of unity with delta z and add additional terms in order to fulfill the front and reverse, front and back faces, so we could get the three-dimensional description. So we derived the mass and momentum equations, and we also began to derive the energy equation and left it at some point. So in this class, let me complete the derivation of the energy equation and show the advantages of non-dimensionalizing the equations for solution, and non-dimensionalize the energy equation that we derive and look at the various non-dimensional numbers and their physical meanings, what it means when a particular number is high or low, or a particular ratio of non-dimensional numbers is high or low. Right? So that's the thing that we'll be looking at today. And if time permits, we'll also start with the planar laminar boundary layer flow and start looking at the governing equations for that. Okay, so that is the plan for today's lecture. So let's begin now with the energy equation. So we'll go back to the whiteboard where we were in the previous class. We had started deriving the energy equation. So we said that the term E, which is the specific energy of the fluid, would be a sum of, we said this U has to be understood distinctly from the U, that is the x component of the velocity that we have been using. So let's call this as CVT, if I would. Okay, or maybe we could call it with U hat, so that it is distinct from this U, the velocity. Okay, so E, or the specific energy, let me also call this as a U, like a hat. So this is specific energy. Let's write this. Okay, so in two-dimensional conditions, the inflow and outflow would combine into this term, right? So del by del T of rho E, which is the rate of change of the specific internal energy per unit volume. So this multiplied by delta x delta y. Okay, so everywhere delta x delta y would get cancelled, and these two are the net inflow and outflow of energy due to advection. So this becomes equal to, what are the terms that would come? One is, of course, the conduction heat transfer that happens. So there is a minus k del T by del x at x here, and minus k del T by del x at x plus delta x here, which would have been minus k del T by del x at x plus del by del x of minus k del T by del x. Okay, or minus k del T by del x here, and this will be plus of k del T by del x plus del by del x of k del T by del x delta x. And when you look at the difference, the k del T by del x gets cancelled, and you get a del by del x of k del T by del x. And similarly here, there will be a k del T by del y at y, and here it will be k del T by del y at y plus delta y, which would be k del T by del y at y plus del by del y of k del T by del y, okay, multiplied by the area. So when I look at that, then I get these two terms. That is because of the conduction heat transfer. In addition to that, there would be work done by the body force terms and the surface force terms. The work done by the body force terms and surface force terms would be nothing but, or rate of work done by, would be the forces multiplied by the velocity components or the rate of change of displacement in the respective directions. So it will be rho times Fx u plus Fy v for the body forces, and it will be again sigma xx u here and sigma xx u at x plus delta x here. So the net work would come in this fashion. So it will be actually del by del x of sigma xx u plus del by del y of tau yx v plus del by del x of tau xy v plus sorry, this is u, okay, and del by del x of tau xy v plus del by del y of sigma yy v in these two directions, plus any heat generation that will be there. Now, in order to simplify this equation into the form that is written here, what we will need to do is, okay, so this term, the left hand side here has this E, which will be u plus a half v squared, and this v is the velocity vector, and that is nothing but u squared plus v squared plus w squared by 2 in 3D, and in 2D this term will not be there, it will be u squared plus v squared by 2. Okay, so now what we do is to consider the momentum equations in the two directions. Okay, so we'll be starting with let's say so these equations. So this is the momentum equation in x direction, and this is the momentum equation in y direction. I take each of these equations. I take this equation multiplied by u, this equation multiplied by v, and add the two together. So what will happen? I'll have a u del by del t of rho u, and there's a v del by del t of rho v getting added together. Okay, so basically the terms that contain the continuity equation will have to be taken out and removed. So let me first go to that. So suppose I write the left hand side of the x momentum equation multiplied by u. So it is u, so momentum equation multiplied by velocity component. Okay, so in this case x direction momentum equation multiplied by x velocity component. So that will be u multiplied by the left hand side of this equation del rho u by del t plus del by del x of rho u square plus del by del y of rho u v. Okay, first of all let us take out the continuity equation from this. What is the continuity equation? The continuity equation is the continuity equation is going to come from here. Yeah, this is the continuity equation. Del rho by del t is equal to okay, my mouse is misbehaving. All right. So the continuity equation is the equation that we have got here, which is del rho by del t, and I have opened out these terms: rho del u by del x plus u del rho by del x, rho del v by del y plus u v del rho by del y, and you get terms of this form, which is d rho by dt plus rho times del u by del x plus del v by del y. And so if I take the continuity equation in this form, okay, and this continuity equation in the form in which it is appearing in this equation. This equation, if I take it and multiply it by u, I'll get a u del rho by del t plus u del by del x of rho u plus u del by del y of rho v equal to 0. So I would subtract that from the equation that we just wrote here. So let's go to the last slide. So this minus u times, I'll continue to subtract the continuity equation, which is del rho by del t plus del by del x of rho u plus del by del y of rho v. What do you get here? So if I multiplying by u, I'll do for the whole thing. So what happens? This is 0. Okay, so you're multiplying by 0 and subtracting, not a problem. So this will be del by del t of rho u, which is rho del u by del t plus u del rho by del t, and subtract u del rho by del t, you get a so that u stays outside. The first term will become del rho okay. So now del by del t of rho u, so minus this one, will become rho del u by del t, rho del u by del t, okay, plus similarly this one, del by del x of rho u square will be u times del rho u by del x plus rho u times del u by del x. So u del rho by del x subtracted, so it will become rho u times del u by del x, plus the same way this will become rho v times del u by del y. Okay, now multiplying by u, I get rho u del u by del t plus rho u square del u by del x plus rho u v del u by del y. Okay, so this is the left hand side of the first equation, that is x momentum multiplied by x velocity component. In the same way, if I do the y momentum multiplied by y velocity component, okay, and add the two together. So the left hand side of that will get added to this v times, I'll get again rho del v by del t plus rho u del v by del x plus rho v del v by del y. Okay, so if I add these two together, then what I get is something like this. It will be rho will be outside, because in both of these terms density is a common term. Density is a common term because it's coming in all the terms. So I can take the density out and take the u in. Then it becomes del by del t of u squared, and this also becomes your del by del x of u squared, del by del y of uv, and so if you add the terms together, then you get rho times del by del t of u squared plus v squared by 2, okay, plus u del by del x of u squared plus v squared by 2 plus v del by del y of u squared plus v squared by 2. Okay, so this will be the left hand side of the x momentum equation multiplied by x plus y momentum equation multiplied by y. Okay. Similarly, if I write the right hand side of this, so what am I doing? I am taking the x momentum equation, which is this one. So the right hand side of this will be multiplied by u. So you will have a rho fx into u. There will be a u del xx by del sigma xx by del x. U del sigma tau tau yx by del a del y. So the z term will not be there. Okay. So that will be there in this equation, and similarly here it will be rho fy into v. There will be a v tau xy by del x, and there will be a v sigma y by y del y. So that will be the right hand side that you will get for this equation. So this will look like rho times u fx plus v fy, this comes from the body force terms, plus u del by del x of sigma xx plus del by del y of tau yx, okay, plus v into del by del y of sigma yy plus del by del x of tau xy. Okay, so this is what you get on the right hand side of the momentum equations multiplied by velocity added up. Now if I subtract this from the energy equation, so the energy equation had this, okay, so on this side this is rho into E, so I can actually now go back to this equation, okay, which gave rise to this term. Okay, so if I take this and if I add continuity equation multiplied by u squared plus v squared by 2, then this rho would go in. So it would be rho times this and rho u times this and rho v times this, because if I add, for example, u squared plus v squared by 2 multiplied by the 0, which is del rho by del t plus del by del x of rho u plus del by del y of rho v. So I'll then get this left hand side as del by del t of rho into u squared plus v squared by 2 plus del by del x of rho u into u squared plus v squared by 2 plus del by del y of rho v into u squared plus v squared by 2. Okay, so this is basically obtained from the momentum equations multiplied respectively by u and v, the x momentum equation by u and y momentum equation multiplied by v, and added together. So you get this. So this is from the momentum equations. So if you subtract this left hand side from the left hand side of the energy equation, which is here, so you have this is rho E, which is rho times this, okay, so which is nothing but this is u plus u squared plus v squared by 2. So if multiplied by rho, I get rho here. Okay, so if I put that in this equation, so or let's not multiply by rho here, just put this into this, then this E is U tilde or U cap plus this. Now I am subtracting this part of it from the main equation. So I'll get rho times E minus U squared plus V squared by 2, which will be U. Okay, similarly this rho U times E minus U squared plus V squared by 2, which is U. So if I subtract the left hand side of that equation from the left hand side of this and right hand side of that equation from the right hand side of this, basically I am subtracting the momentum equation multiplied by velocities from the energy equation. Then I'll get the thermal energy equation, because what I have got here is basically the left hand side has the transient advection and diffusion of the kinetic energy, flow kinetic energy, and so I subtract the flow kinetic energy from the main energy equation. So energy equation minus velocity multiplied by momentum equation would actually give me left hand side will be del by del T of rho U plus del by del X of rho U plus del by del Y of rho VU, which I can actually call it as du rho times du by dt. Okay, because if I separate this out, I'll be able to get let me expand this first and then write it. So this is equal to rho times del U by del T plus U del U by del X plus V del U by del Y, okay, which is basically one part of it. The second part of it will be plus U times del rho by del T plus U del by del X of rho U plus del by del Y of rho V, and this is 0 by continuity equation, because continuity equation says this plus this plus this is 0. So it will basically be this term, which can be called as rho times du by dt. So the left hand side is now simplified to just one term, which is d by dt of u, where d by dt is nothing but del by del t plus u del by del x plus v del by del. So that is your the basic definition. So this is this. So the left hand side of the energy equation now becomes equal to rho times d by dt of the internal energy you had. Now what happens to the right hand side? Now the right hand side, let's go back to the energy equation and this equation and look at it. So the right hand side of the energy equation has a conduction term which would stay as it is. This term has rho fx u and fy v, and the corresponding term in the other one is also the same, so they would get cancelled out, and these terms would have so this would be you can split it into u del by del x of sigma xx plus sigma xx del u by del x and so on. So the u del by del x of sigma xx term would get cancelled, and sigma xx del u by del x will remain, tau xy del u by del y will remain, and so on. So that is the thing that you will get in the equation, because your right hand side here ufx plus vfy into rho, they get cancelled out and these terms get subtracted out. So you get sigma xx del u by del x and tau xy del u by del y, that will remain in the equation. Okay, so that is what we will get. So the right hand side will look like del by del x of k del t by del x. The conduction term will remain as it is because that has nothing to subtract out from there. Del by del y of k del t by del y, that is a term that will remain as it is, plus you will get sigma xx del u by del x plus tau yx del u by del y plus sigma yy del v by del y plus tau xy into del v by del x. Okay, so these are the 4 terms that will remain out of the 8 terms that actually come out of this. Okay, this equation here, the right hand side, this gets 2 terms, this gets 2 terms, this gets 2 terms, this gets 2 terms, out of which the 4 terms that contain u sigma xx del sigma xx by del x, u del tau x, they'll get cancelled out. So the other terms that remain is sigma xx del u by del x, tau yx del u by del y, then sigma yy del v by del y, and tau xy del v by del x. Those are the terms, and this q gen term will remain. Okay, plus q dot generation. Now these terms, if you took a look at it, they will have a pressure term in these two, which would come out as P del u by del x and P del v by del y with a minus sign, because sigma xx, as I showed you in the Stokes equation, has this minus P here, and sigma yy has a minus P here. So there will be a minus P into del u by del x plus del v by del y that will come, and then this term multiplied by u, and this term multiplied by v, and this term correspondingly multiplied by the u and b, that will be there in that equation. Okay, so go back to this one. So this sigma xx will have 2 del u by del x minus 2 by 3 del dot u multiplied by del u by del x, and this will be that, and so you get this, let me write it as del dot k del t. Okay, so that is that, plus q dot generation, which stays as it is, plus let me write it with a minus sign because the pressure has a negative sign in both the terms. So I'll get minus p times del u by del x plus del v by del y, because that is going to come out of this sigma xx and this. And this tau x and tau xy are the same, so you get a del u by del y plus del v by del x there, multiplied by this. So tau xy itself is a, so let me write the other terms in sigma xx and 0, so it will be 2 mu times 2 del u by del x minus 2 by 3 into del dot v, which is del u by del x plus del v by del y, and multiplied by del u by del x. Okay, so that is this term, plus I'll write this one, which will be mu times 2 del v by del y minus 2 by 3 into del dot v. Okay, so that is this term, and this term will be plus del u by del y plus del v by del x multiplied by, this also has a mu which will come here, and this tau xy and tau yx are equal to again del u by del y plus del v by del x. So what happens here? This becomes this the whole square. Okay, so So I can write it the whole square and remove the second one. Right? So that is one part of it. The other part, here again, I can gather terms. So there will be 2 del u by del x the whole square. Okay. So let me write this is equal to mu times del u by del y plus del v by del x whole square we have got plus, so mu I'll keep it outside here. So there will be twice of del u by del x the whole square plus here similarly there will be there is a del v by del y here. So plus twice del v by del y the whole square. So I can actually keep this 2 outside and write this. So this term is done and this term is done. Now what is remaining is del dot v. So minus 2 by 3 into what is del dot v? Del u by del x plus del v by del y, and that multiplied by del u by del x plus del u by del y. So you get a del u by del x plus del v by del y the whole square. Okay, so this what we call as this term, the whole thing in the braces, we call it capital phi. So you get a mu phi, which is going to come to this one. So this you can replace by mu phi in this equation. So all what is below that gets gathered under mu phi. So this is your right hand side of the energy equation. Right hand side of the energy equation becomes equal to just del dot k del t plus q dot gen minus p into del dot v. This is del dot v. Okay, plus mu phi. So the energy equation can now be summarized. The left hand side is rho del u by du by dt. Okay, so let's go to the next page. So you get the energy equation finally as rho du by dt is equal to del dot k del t plus q dot generation triple prime plus mu phi minus p into del dot v. So this is finally your energy equation. Now it is always more convenient to write it in terms of Cp rather than Cv. So we use this relationship. H is equal to U plus PV, which is P by rho. Okay. So if I take the total derivative, I get dH by dt is equal to du by dt plus P by rho. It will be 1 by rho dP by dt minus, so this P would remain here and 1 by rho would become minus 1 by rho square d rho by dt. Okay, so if I substitute for du by dt, then du by dt, which is the left hand side, rho du by dt would be equal to rho dH by dt. Okay, and the other terms will come here, the minus 1 by rho dP by dt plus P by rho square d rho by dt. Right, so this is the thing that you would get, and on the right hand side you get this. So this P del dot V term and this one actually we can combine. So if I bring the P del dot V term to the left hand side plus P del dot V to the left hand side, that will be equal to del dot K del T, okay, plus Q dot generation plus mu phi. Now if I look at these two terms, I can write it's equal to, I can take out the P, and by rho squared also I can take out. Then I'll get d rho by dt plus this term. I have taken a P by rho squared out. Okay, so this has to be multiplied by rho. So there is a rho that comes here and there is a rho that comes here. So one rho gets cancelled out and this rho goes off here. Okay, so when the multiplying by rho, I have done only one term. So then this is that. So this is not P by rho squared, it's P by rho. So there will be a rho del dot V. Okay, and this from continuity equation we know is 0, because in the continuity equation derivation we wrote that the continuity equation is equal to d by dt of rho plus where is that? We have got some more pages. Yeah. Yeah. So in the continuity equation we said that d rho by dt d rho by dt. So d rho by dt plus rho del dot v. Okay. So d rho by dt plus rho del dot v is equal to 0 is what we showed here, and that is what we are now going to use in the last page. Okay. So that is in the last expression that we wrote. D rho by dt plus rho del dot v is 0 by continuity equation. So accordingly, this plus this term vanish, and therefore you only have dH by dt into rho is equal to this. So this dP by dt term can come to the right hand side. That will be my final form of the energy equation. Okay, so let me erase this part of the equation so that I can make space for writing the energy equation in the form of enthalpy. So I can write the energy equation as rho dH by dt is equal to okay, this dP by dt go to this right hand side. So I'll have del dot K del T plus dP by dt plus Q dot gen triple prime plus U phi. That is the thing that typically comes out, and actually I missed out on one term in this whole process in writing in writing this one. Actually dH by dt is not just this, but there will be one more term that will come, because H is a function of both pressure and temperature. So dH by dt is del H by del T into since H is a function both of temperature and pressure, in writing the energy enthalpy term, we will need to write dH is equal to so from this term itself we can go to the next step. dH is del H by del T into dt plus del H by del P into dP, and this we know is Cp, and this from the Maxwell relations we should be able to show that this is going to be equal to 1 minus beta T by rho, where beta is the volumetric expansion coefficient and rho is the density. So if I say that, then this will be equal to 1 minus beta T by rho into dP plus Cp dt. So if I write rho d, this is H and this is this rho dH by dt will be actually equal to, I can write it in terms of this, the first this term would become rho Cp d by dt of Cpt in this one, and in the other term the rho would get cancelled out, and you will get a plus 1 minus beta T into dP by dt. So now this on the right hand side is equal to del dot K del T plus Q dot triple prime generation plus mu phi plus dP by dt dot. So this dP by dt would cancel out with this 1, and this beta T would come to the right hand side. So I'll get rho d by dt of Cpt would actually be equal to del dot K del T plus Q dot triple prime generation plus mu phi plus beta T into dP by dt. So this is the other form of the energy equation. So you see that the energy equation has multiple forms now. This is one form of the energy equation. So let's call this as let's say form A. This is the one that we wrote in the previous page, is another form of it. So I'll call this as B, and in terms of U that you wrote is another form, which we call it as C. So we have now so far got 3 different forms in which the energy equation is finally written down. So those are the things that we need to bear in mind. So these are the multiple ways of writing the energy equation. So this is where we reach now. Now, using this energy equation, if we try to use the concept of non-dimensionalization, then we'll be able to use the same energy equation for multiple self-similar geometries, and we also can understand the meaning of the non-dimensionalization and its use. So suppose I have some object whose characteristic dimension length is L, and there is a flow that comes in at a velocity u infinity and temperature T infinity and density rho infinity. okay, and pressure P infinity. Now, if this is the condition with which this comes, then I can actually normalize the x direction, y direction, these two length directions I can normalize with respect to the length. The velocity u and v I can normalize with respect to u infinity. Okay. Similarly, the temperature T I can normalize with respect to the temperature difference T minus T infinity divided by so if this body has a surface temperature of, let us say, T wall, then it will be T minus T infinity by T wall minus T infinity will be the non-dimensional form of temperature theta. So if I try to use all of these, then I would get these equations simplified to a substantial extent. So let me write that expression. So I am writing the governing equation in the form in which I finally wrote it. So if I write it expanded, then I'll get, if I take a constant Cp, then I'll get a rho Cp del T by del T plus U del T by del X plus V del T by del Y. Okay, so this is your left hand side, and this is equal to, if I again take a constant K, it will become K del squared T by del X squared plus del squared T by del Y squared. Okay, so I'm just taking constant Cp and K conductivity. Okay, so with that I get this plus beta T multiplied by del P by del T plus U del P by del X plus V del P by del Y. Okay, so this is dP by dt, this is dt by dt. Okay, plus Q dot generation triple prime plus mu times, we'll write twice del U by del X whole square plus del V by del Y whole square minus 2 by 3 into del U by del X plus del V by del Y whole square plus del V by del Y, del V by del X plus del U by del Y whole square. Okay, so this is three terms that we had in the phi. So this is your complete form of the energy equation. Now let me try to use these variables, which is capital X is equal to X by L, capital Y equal to Y by L, capital U equal to U by U infinity, capital V is equal to V by V infinity, and theta is equal to this. Then I'll be able to try and normalize all of these equations into the forms which are non-dimensional. So each of these terms will be then non-dimensional. So the problem then can then be used for objects of any dimension which is similar to each other. So suppose I have, for example, a small object of the same shape whose length is shorter than this is the length, and a longer object whose length is this, the same results will be applicable to both. That's the way we be able to solve the equation. So you don't need to solve the equations for every dimensional case, but it can be valid for a family of cases which have similar dimensions. Okay, so we'll be normalizing that now. So for that, let's now for time tau would be non-dimensional t. So this is t divided by the length scale of this would be L by u infinity. Okay, so it will be u infinity L by u infinity t by L will be the non-dimensional time coordinate which will be used for that t. This is these things will be x and y. So let's go to the next page and start writing this one. So del by del t, rho by rho infinity. Okay, so rho, let's first write one term at a time. So rho del by rho Cp del t by del t is the first term. This can be written as rho by rho infinity into rho infinity, okay, into Cp okay. So if I just try to normalize temperature in terms of theta, so I'll write a del theta by del tau. So what does this tau become? This tau is t u infinity t by L is equal to tau. So if I write a tau here, tau into L by u infinity t, so there will be a L and a u infinity t. U infinity will be, so the t will be tau into L by u infinity. So tau into L by u infinity is t, and similarly this theta is actually d theta is the same as dft minus tw. So there will be a t wall minus t infinity that will come here. This multiplied by the rho Cp which already stays there. Okay, so this will be the first term. What about the second term? The second term will be rho Cp into u del t by del x. This can be written as the same rho Cp will just remain the way it is. This u will become capital U multiplied by u infinity, and this del t by del x will become del theta by del capital X, and this capital X is nothing but L times small x. So there will be L into capital X into small x. This L will come here, and this thing will have t wall minus t infinity here. Okay, so in all of these terms, basically you get the same combination of additional terms. You get a rho Cp u infinity by L into t wall minus t infinity. So it's rho Cp u infinity by L into t wall minus t infinity. Similarly for the third term also. So if I write the left hand side, it will be rho infinity, rho into Cp into u infinity into t wall minus t infinity divided by L. So this is what you have on the left hand side. Then the common terms will be del theta by del tau plus u del theta by del x plus v del theta by del y. So this is what you would get on the left hand side. And on the right hand side, the first term would be k into del squared t by del x squared plus del squared t by del y squared. Okay, so this would be equal to, now the k would remain the way it is, and by x squared and by y squared will have by L squared here, and there will be a t wall minus t infinity multiplied by del squared theta by del x squared plus del squared theta by del y squared. Okay, so this is the next term. And similarly, the pressure term, beta t is already non-dimensional because beta is 1 by v dv by dt, and v gets cancelled. So this is 1 by t dimension. So beta t is already non-dimensional, multiplied by del p by del t plus u del p by del x plus v del p by del y will be, if I just normalize the other terms, p would automatically get non-dimensionalized. So I'll get this would actually have a u infinity. So beta t would stay there, u infinity by L, right? So this whole thing would get normalized like that. This will be del p by del tau plus u del p by del x plus d del p by del y, del capital Y, sorry. Right, so this stays like that. And what are the other terms? There is a viscous term and the Q dot generation term that are there. Let's go to those. So mu phi term would be equal to, the mu would stay the way it is, and phi, basically there is a del u by del x the whole square, so there will be a u infinity square divided by L square. That will normalize the whole thing, twice del u by del x the whole square to the capital del u by del capital X plus del v by del y the whole square. So all the terms will have the same dimension, minus 2 by 3 into del u by del capital U by del capital X plus del capital V by del capital Y the whole square, and the third term would be plus del V by del X plus del U by del Y the whole square. Okay, so if I put all of these terms together, if I bring from the left hand side, so the left hand side has rho Cp u infinity by L. Okay, rho Cp into u infinity by L into T wall minus T infinity. If I take it to the right hand side, then the left hand side becomes plane and plane here. So it will be del theta by del tau plus u del theta by del x plus v del theta by del y. If I keep that on the left side and take the other term to the right hand side, then that will multiply each of these terms in the reverse. So if I combine the two, combine the equations, I'll get del theta by del tau plus u del theta by del x plus v del theta by del y is equal to, okay, so on the right hand side you will have rho Cp u infinity by into T wall minus T infinity into L. So this is the term that is going to multiply the whole of the right hand side. This multiplied by the first term would be k into T wall minus T infinity divided by L square multiplied by del squared theta by del x squared plus del squared theta by del y squared. Okay, so now this combination gives me something. Then I'll have this whole thing multiplies everything on the right hand side. So this is the first term plus the second term is Q dot triple prime generation, which we did not do anything to, plus the third term, which will be the pressure term. The pressure term had beta T into U infinity by L. Okay, so it will be beta T into U infinity by L multiplied by del P by del X del T plus U del P by del X plus V del P by del Y. In this, everything else is non-dimensional other than the P, which will automatically get normalized when this multiplies this, plus the mu term will be mu U infinity square by L square multiplied by this whole term. Okay, so the one term in the bracket, this is the braces that are there, this whole thing will come under this. Okay, now if then this with this bracket closes. So what are the terms that I will get? I'll get this combination, which will be the L squared will become 1 by L here, the T1 minus T infinity will get cancelled, so it will be K divided by rho Cp U infinity into L. This is the term that I would have. So this K by rho Cp we know is alpha, so I get U infinity L by alpha, which I can write it as U infinity L by nu into alpha by nu. So what happens? This is 1 over Re, the Reynolds number, which is U infinity L by nu, and this nu by alpha is called the Prandtl number, which will be 1 over Prandtl. Nu by alpha is Prandtl, so this is, so this combination, this and this, basically gives me a 1 over RePr which will replace this term, this combination. Okay, so this is one set of non-dimensional numbers that I get for this, where how do I understand this? Re is U infinity into L by nu. This normally we write it as U infinity squared by U infinity by L into nu. So this is how we write this. So this U infinity square is nothing but, so if I want to write a rho U infinity square, and there is a rho nu, this rho nu will become actually mu. Okay, so this rho U infinity square, so rho U is the mass per unit area, mass flow rate per unit area multiplied by U infinity, so this is a momentum. So this term stands for the inertia of the flow. Okay, so this is nothing but m dot into U infinity by unit area. Okay, so if I multiply both by area, this as well as this by area, so I get rho into U into A, it will be mass flow rate, m dot into U infinity on the thing, which is basically the momentum, and here you will have mu A into U infinity by L. This U infinity by L is a velocity gradient, multiplied by mu is a shear stress, and so this A, so this is the viscous force. So you get this Reynolds number as the ratio of the inertia forces divided by the viscous forces. Okay, so this Reynolds number basically stands for the ratio of the inertia to viscous forces. So when the Reynolds number is large, then the inertia forces dominate over the viscous forces. Otherwise, the viscous forces dominate over the inertia forces. That is one part. And Prandtl number is the ratio of the two diffusivities, nu, which is a momentum diffusivity, and alpha, which is thermal diffusivity. So it's a property of the fluid, and when Prandtl number is large, then the momentum diffusivity is much higher than the thermal diffusivity. So the fluid is more viscous than conducting, whereas when the other way around, alpha is much greater than mu, and the Prandtl number is much less than 1, then it is more conducting than viscous. So liquid metals fall under very low alpha very low alpha values, which actually are not so viscous but very highly conducting. But oils, which have large viscosity, fall under large Prandtl numbers, and gases have Prandtl number of the order of 1. So this Re and Pr therefore are representative of inertia to viscous force ratio and the ratio of thermal diffusivity, momentum diffusivity to thermal diffusivity. So that is one term that we would find. The second term that we will find is this multiplied by this. So the L gets cancelled, U infinity gets cancelled. So you get beta T multiplied by 1 over rho Cp into T wall minus T infinity. Okay. So now here you have a dimensional pressure. So if I have to non-dimensionalize the pressure, I'll normalize it. So if I write capital P is equal to the P divided by rho U infinity square, then if I write this as P, there will be a rho U infinity square that will come here. So the rho would get cancelled out. So you would get this U infinity square here, which is the inertia, and Cp T wall minus T infinity, which is the thermal forces. So this is basically the ratio between kinetic energy in some sense and thermal energy. So this number is usually called the Eckert number. Eckert is another heat transfer scientist. So you will basically write Eckert number multiplied by this in terms of all non-dimensional numbers. Okay, and the last term, which is there, so Eckert number is the ratio of the kinetic energy to thermal energy. So that is the ratio that you would get, and the last value or the last ratio that you would get is this mu U infinity square by L squared multiplied by the opposite, which is L by rho U infinity Cp into T wall minus T infinity. So if you see there is an L getting cancelled here and there's a U infinity getting cancelled here. So here you get a different combination of numbers. So if I still write if I, instead of cancelling it out, if I write U infinity squared divided by Cp into T wall minus T infinity as Eckert number, then the rest of the number that you would get will be rho U infinity L by mu is what you get. So you would get Eckert number divided by the Reynolds number. Okay, so this is basically the same combination that you get. So this number will become Eckert number divided by Reynolds number. So if I complete this equation in the non-dimensional form, then I'll get del theta by del t plus u del theta by del x plus v del theta by del y is equal to 1 over REPR multiplied by del squared theta by del x squared plus del squared theta by del y squared plus the q dot gen will get normalized in the same fashion as we saw it last. So this will be q dot gen multiplied by L divided by rho u Cp rho Cp u infinity into T wall minus T infinity. So that will be your non-dimensional q dot gen triple prime into L divided by rho u Cp rho infinity Cp into T wall minus T infinity. Okay, so basically you can actually put an L cube divided by L square here. So this is volumetric heat generation rate multiplied by this. So this is the total heat generation rate per unit time, and this is the heat flow per unit time, because that's rho UA multiplied by Cp to T infinity, so m dot Cp T infinity. So this is basically the ratio of heat generation to heat flow. So this is that term, plus you get Eckert number multiplied by del capital P by del tau, this is tau, sorry, plus U del P by del X plus V del P by del Y, okay, plus Eckert by Reynolds number multiplied by the non-dimensional phi value. Okay, so what this shows is that the viscous term has this REPR multiplying it, okay, and the Eckert number multiplies what is called, this is the viscous term, okay, and this is the advection term, this is the transient term, okay, and this is the heat generation, this is the pressure work, and this is the viscous dissipation. So how do we understand these terms? So this term stands for advection due to fluid motion. This is the rate of change of energy in a control volume. This is the term that is because of conduction. This is the conduction term. We call it, okay, this is the conduction term. Okay, the conduction term. And this is the heat generation term. The pressure work term will be important when the Eckert number is significant. When the Eckert number is extremely small, then the pressure work would not be significant. And what is Eckert number? Eckert number is a ratio of kinetic energy, or U squared, U infinity squared, to CPT. So only when the velocity becomes substantially large does U square become anywhere comparable to CPT. For example, if we're talking about flow of air, the CP is around 1005 joules per kg Kelvin. So if I'm looking at Cp into T-wall minus T infinity, which is, even if it's 5 degrees Celsius difference, so it will be about 5000 joules. Okay, so that's what we will be looking at, joules per kg. That is the thing that we are looking at. In order to produce this, the U squared that is required will be square root of 5000, or U that is required will be square root of 5000, which will be a large number, right? So a square root of 5000 is about 70, right? So 70 meters per second is the kind of velocity that is required in air in order to make about 4 to 5 degrees difference in temperature. So only when U square is very large does this produce any significant effect, otherwise it's not. So the Eckert number shows that only with high speed flows we have the importance of pressure work, otherwise pressure work is not important. So the pressure work term is normally important in high speed flows. And this one is important when EC by RE is significant. So if Reynolds number is very small and velocities are large, this is not a combination that is possible because Reynolds number also goes with U. So it's EC by RE. So the viscous terms should be extremely important because this is inertia by viscous. So U squared by CPT. So the term compared, it's actually significant in flows with very large temperature gradients and very large velocity gradients and very high viscosity. So EC by RE becomes important in such a term, in which case the viscous dissipation becomes important. For example, in the case of bearings in high-speed shafts, the dissipation of kinetic energy into heat becomes an important term, and that is when the viscous dissipation is important. Otherwise, these parameter combinations, EC by RE determines when viscous dissipation is important, EC alone determines when pressure work is important, and REPR determine how much the advection is dominant over diffusion. If REPR is large, then advection is very dominant because this term becomes large and this is going to be reduced substantially. Or if REPR is small, then this term is of similar magnitude as this. So this is the way we look at it. So the non-dimensional numbers actually give you an information about which terms in the key equation need to be kept and which terms can be dropped for the analysis. Okay. So with that, I will stop here. Today's lecture has become a little more long as compared to the usual ones, but it was necessary to take you through the entire process before we could stop this lecture. So I'll close this lecture here, and in the next class we'll look at the external flows. We'll be basically looking at the flows over the external flows over bodies in the next class. So we'll stop here.